Today we are going to talk about the calculation of the band structure of aluminum. And we're also going to talk about the calculation of the density of states of it. So here in step 1, we are going to relax the geometry. And you can see from here, I'm giving you the primitive scale for the face-centered cubic structure, FCC. You have only one atom in the FCC structure. And here I give the picture showing you the three lattice vectors for FCC. It's A1, A2, and A3. And so in the Cartesian coordinates, the A1 and A2 and A3 lattice vectors are listed here. A non is a lattice parameter of aluminum FCC structure. Since we have only one atom in this primitive cell, so this atom is shown here. And here I give you the Abinit input file for doing the geometry relaxation. You can see here I put the LPT cell equal to 2 so that I also relax the lattice vectors of this cell. We are using the PW method for the calculation, so the E cut is very low. It's only 500 electrovolts. And since we have only one atom in the simulation box, so you see I have only one atom here, and the fractional coordinates for this atom is 0, 0, 0. And the lattice parameter A1, A2, A3 is defined here. You can see that for the A1 is half, half, 0. So that's corresponding to half, half, 0 here. And A cell corresponding to the A non. And after the relaxation of the geometry, the A cell parameter will be relaxed to the optimal value. Because this is a metallic structure, so we need a high density of the key points in the calculation. I use 16 by 16 by 16 key point mesh for this calculation. And in order to construct the band structure, I showed you the first Brillouin zone for this FCC structure. In many cases, we draw the band structure along the high symmetric key points in the first Brillouin zone. And so here in this figure, I list several high symmetrical points. They are the gamma points, K point, W points, X point, L point, and the U point. And so we are going to draw the band structure along those red lines. In this table, I also gave you the coordinates for those high symmetrical points in the first Brillouin zone. So this picture follows the reference 1, which is given at the end of this PDF file. So once we finished the geometry relaxation and we got the equilibrium lattice constant for aluminum FCC structure, which is a 4.0414 angstrom. And so in the next calculation, I just plug in this equilibrium lattice constant into the Abinit program, and which is a 4.0414 angstrom here. So in the first part of this calculation, I just perform Kongshan DFT simulation on this aluminum FCC structure. In the second part of this calculation, I do a non-self-consistent Kongshan DFT simulation, which means that I just use the Kongshan potential from the first part of the simulation and then resolve the Kongshan equation for many key points here. We solve it for many key points here because we want to construct the band structure. So the key points we are going to solve here are described here. And so two important keywords for constructing the band structure is NDVK and the key point bounds. You can look up them in detail on the Abinit website. So basically speaking that this N DFK determines the resolution of the calculations along each line segment on these red lines. And these key point bounds define each point along the line segments. So you can see from here, the first point is a gamma point, which is 0, 0, 0 in the first Brillouin zone. And then we go to the X point, which is a half, 0, half, which is a half, 0, half, which means that we are going to first do the line segment between the gamma point and the X point. The next point in this key point bounds is a half, quarter, 3/4, that's a W point, and which is here. So which means that the second line segment we are going to do will be from X to W. After defining all the line segments with the key point bounds parameter, then we run this calculation, and so the eigenvalues of all the bands along those line segments will be outputted in this file. And here I give you the first several lines of this eigenvalue file. And you can see that it will list the key point index and also tells you that how many bands we have in the calculation. So here we have 3 bands for this case, and also the weight for each key point, and also the reduced coordinates for the key point in the first Brillouin zone. And after that, you get the eigenvalues for these 3 bands for this key point. Apparently that once we want to plot the band structure, we only need these 3 values, which are corresponding to the eigenvalues of the 3 bands at one key point. So we can extract them by using this awk command in Linux. And so we can extract all the eigenvalues here. You see that now we only have 3 columns, and each column corresponding to 1 band in the calculation, and each line corresponding to 1 key point in the calculation. By giving these 3 columns data to the EE variable in MATLAB, and so then I can plot the band structure by using this MATLAB script. After the plot, you will get this graph. And you will see that actually in the MATLAB program, I did not really label these special points in the first Brillouin zone. So I labeled them afterwards with some plotting program. And you can do them by yourself as well. And we know that, in order to do this, and we know that the first point we are going to label will be the gamma point, because gamma point is the first point we define here for the key point bound command. And the second point will be the X point, which is here. The next point will be the W point, and which is here. And after the W point will be the key point, which is here. You can also see from this graph that the resolution on each line segment is 50. We have 50 different key points on each line segment. So that's why the index go from 0 to 50 to 100 to 150 to 200 in this way. It is 50 because for the n divide k keyword here, we define it as 50. In the third part, we discuss how to calculate the density of states. It's straightforward to calculate the density of states in ABinit. You just need to put this print dots keyword in the input file. And one thing I want to point out is that the graph of the dots is sensitive to the number of the key points. So that's why I increased my key point mesh to 20 by 20 by 20 in the calculation. In practice, you need to increase your key point mesh to a point that you have a very nice DOS picture. And after the calculation, Abinit is going to write the DOS into this file. And here I give you a snapshot of this DOS file. The header of this file, including the information of the calculation, as long as the Fermi energy of this calculation. And the second part of this file contains the DOS. We should just be interested in the first two columns here. The first column is energy axis in your plot. The second column is the DOS. So here I give you the MATLAB script for plotting the DOS. Once you use this command to load this data file, you need to remove the headers here. So this is a picture I generated by plotting the first two columns of that file. And you can see that I also draw this vertical red line here to show the Fermi energy of my system. And aluminum is a metallic system, which can be seen from the DOS file, which means that your density of states is non-zero at the Fermi energy. And hopefully this tutorial is helpful for you to draw the band structure of solids and also density of states for the solids. And thank you for watching, and see you next time. Bye-bye.